All right, last part of tonight's discussion, or today's discussion, depending on when you're watching this. We've got, we're going to be asked to graph y is greater than negative 2 over 3 x plus 1. Let's go ahead and zoom in on that real quick. All right, so here's what we know. This is going to be, this is an inequality, so it has a whole bunch of solutions. Those solutions are going to be separated from their non-solutions by a line, just like we saw the solution separated from non-solutions by a boundary here. The boundary that will separate the solutions from the non-solutions will always be given by what we call the related equation. And the related equation is just the inequality with the inequality symbol replaced with an equal symbol. So for us, for this inequality, the related equation is y is equal to negative 2/3 x plus 1. So we can graph that boundary real quick. Y-intercept is 1, slope is negative 2 over positive 3, negative 2 over positive 3, or positive 2 over negative 3, positive 2 over negative 3. All right? But we don't want to sketch that line right away because we have to think about whether the points on that boundary are going to be solutions. Right? If you can't quite understand the conceptual explanation of this, which I'm about to give you, one of the ways that you could tell just really easily by brute force is take a point from the boundary and plug it into the inequality. Right? If we took a point like, say, what is that, 0, 1, and plug it into the inequality, we would have 1 is greater than negative 2/3 times 0 plus 1, which would be 1 is greater than, this would all be 0. So we would just have 1 is greater than 1. This is false, right? Which means the values on our boundary here are not solutions. But that should have already kind of made sense to us because the values on this boundary are the values where the two sides of the equation are going to be equal to each other. They're going to have the same value. Our inequality in this case says that the left-hand side has to be greater than the right-hand side. If we're looking at the points on the boundary, they're the points where the two sides are equal. That by definition means that the left-hand side is not greater than the right-hand side. So all of these values have to be non-solutions. As we talked about before, the way that we can show that this boundary exists but that it's not made up of solutions is simply by, instead of drawing a solid boundary, sketching in a dashed boundary. Now that I have my boundary, the question becomes which side of my boundary has solutions. There are lots of bad ways to know this about memorizing tricks about greater than symbols and less than symbols and where you shade and where you don't shade. The only warning I'll give you is if you think you can tell which way to shade just from looking at this, I would encourage you to look at these two previous examples and see if it fits those. If you can figure out why it doesn't, then you're welcome to use your handy little trick. All right, but here's what I would recommend. Take a point, plug it in. The easiest point to plug in, the easiest point to check is 0, 0. So let's see if 0, 0 is a solution to this inequality. My inequality says y has to be greater than or equal to negative 2, or just greater than negative 2/3 x plus 1. When y becomes 0 and x becomes 0, this inequality says that 0 is greater than 1. Is that true or false? Right, obviously 0 is not greater than 1. This is false. What this means is that 0, 0 is a non-solution. Because 0, 0 is a non-solution, we know all of the values on this same side of the boundary are non-solutions, which means all of our solutions are on the other side of the boundary. You guys may notice that I'm shading in quotes there, by simply drawing lines. Do that, please. There are a few reasons why. One, it's much easier to erase if you're working in pencil than if you color in. Also, it takes less time. Also, it's easier to read what's happening underneath, which is going to be important for us later when we get into systems of inequalities. All right, one last little thing to look at here. Write the inequality whose solution set is graphed below. All right, our boundary here has a y-intercept of 1, 2, 3, 4, 0, 4. And it has a slope of, let's see here, no, 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 yes. Our rate of change here is going to be 5, down by 5, right by 3. So our rate of change, our slope, is negative 5 over 3. So our related equation here, is going to be y is equal to, we've got a slope of negative 5/3 x and a y-intercept of 4. All right. Then we have to look at whether we have a dash boundary or a solid boundary. We have a solid boundary here, so we're either going to have, so the solid boundary tells me that we're going to have either the less than or equal to or the greater than or equal to, because we need those boundary values to be solutions. We need them to accept, we need the inequality to accept the equals. Then the last question is, well, which one of these two things? And there are lots of different ways to figure this out. Here's what I would recommend. Write your inequality without the inequality symbol in it. Right? Then take a point, any point. I like to take 0, 0 when it's not on the boundary, which it isn't in this case. So I've got 0 is something compared to negative 5/3 times 0 plus 4. Question for us though. Do we want for our inequality 0, 0 to be true or false? Down here, do we want the inequality to be true or false when we plug in 0, 0? Because we're in the non-shaded region, we want that to come out to a false statement. So when I plug in 0, 0, I want this to come out false. When I simplify what I have here, I have 0 is blank compared to all this is just 0, so we have 4. I want this to be false. Which one of our two inequality symbols makes this false? Well, 0 is less than 4, so if I want this to be false, I want to use the greater than symbol. So we can have a false statement which would match the graph where 0, 0 is in the non-shaded region. Right. We're going to come to class and we're going to practice these ideas, but be ready to ask your questions.